your talk.
Thank you very much, René. I'm very happy to be here, and I'm honored to be here, to be invited to speak about my research. And I'd like to tell you about automated static program analysis via constrained term rewriting. So I'm interested in term rewriting, but I also see it as a vehicle to be able to analyze more than just term rewriting. So to give you an outline of my talk, well, first I should explain the title of the talk. So static program analysis, what's that about? Then constrained term rewriting, which is my means to the end of static program analysis. And in the last two parts, I would like to tell you about my recent research published at FSCD this year and at WPTE about various ingredients to such a static analysis. So first things first, what is static program analysis? Well, with software, we have an ongoing problem already over many decades. It's actually not all that easy to get it to do exactly what it should be doing. And quality assurance, there are two main approaches, I would say. The first approach is one that I also teach my students in the programming module, namely dynamic analysis is the fancy term, well, testing. Run the program on example inputs. The goal is to, first and foremost, to find errors. The downside is you need to choose the test case as well. And in general, you don't get a guarantee for absence of errors. The alternative that I'd like to discuss today is static analysis, which is about analyzing the program text without actually running the program. The benefit is that we get stronger guarantees of correctness, which can be important for safety critical applications. I imagine that most of you will have come to the conference by airplane. It's quite likely that some form of static analysis was involved in certifying that airplane fit for travel. You've probably you're aware of the first flight of the Ariane 5 rocket, which triggered stronger interest in static analysis, and in particular in automating the static analysis. Because back there, they had cut corners in the analysis. Having an expert verify program code is expensive. So what I would like to push in my research is the use of automated reasoning techniques for static program analysis. So from the user's perspective, where user is programmer, so they don't want to know anything about all the fancy math that underlies a static analysis tool. They'd rather just use a static analysis tool as a black box. So what properties might we want to analyze? Well, a property that is of my personal interest is program termination. So the question, will my program give an output? Am I guaranteed to get an output if I provide it with some input? Even if I'm very, very unlucky and provide a really nasty input, I still want to get an output eventually and the program to terminate and give control back. More a refinement of termination that we heard about earlier is complexity, namely the use. How long does it take for the program to terminate? So it's all good if the program terminates eventually and I get a guarantee for that, but that may take a million years and I don't have so much time. So I'd like to know, can you give me some more concrete bounds on how long will the program run? And similarly, as it's running, how much memory might it end up using? Because also there, even if I have the time to wait, my computer might not have the memory to run the program until the very end. Another question that is very useful and can be used for many different properties is equivalence. The question, I get two programs, maybe an old version of a function and a refactored version of the function, and I want to know, do these two programs always produce the same result? So that is useful to validate the correctness of refactoring, useful for checking that a compiler optimization has had a correct outcome in a specific case. It can be useful for automatic grading of student exercises. There are many applications. And another question that frequently comes up specifically in rewriting and more generally in languages that support non-deterministic rules or commands, does a single program always produce the same result? So Khristiakiev put it very nicely in their PhD thesis when they said confluence is a property that establishes the global determinism of a computation despite possible local non-determinism. So maybe on the way to the results, there can be different paths that the computation may take, but in the end, we want the same overall outcome. Again, compiler optimization is a topic where this can be applied. Does the order of applying these optimizations matter? Or can I apply them just in no matter what way? More properties. Safety. So safety, well, is important because termination tells you will get an answer, but it doesn't tell you anything about whether it's the right answer. If I'm just supposed to write a program that's terminating, that's very easy. Return 0, you have an immediate answer. It may just not be what you're expecting. So an important safety property is partial correctness. Will the program always produce the right result? Similar, the programmer may sprinkle into their code assertions, assert statements, where the programmer wants the computer to be able to double check. Here, I think that value x, which may well be for the age of a person or for the length of something, should be positive. And ideally, we would be able to say once and for all, yeah, that will always hold. A safety property that has every now and then made it into the media even is memory safety. Are my memory accesses always legal? So if I have this snippet of code in the C programming language, it has the downside. We're trying to write to a memory location that hasn't been allocated according to the C standard. That's undefined behavior. And as compiler engineers will be happy to tell you nowadays, undefined behavior, that's the programmer's fault. Now, anything is allowed to happen, and we insist on our rights that the compiler may generate such code. So the resulting code may well replace all the files of the computer with some weird pictures. You may get information leaks. So remember the Heartbleed OpenSSL attack that did go through the media. And well, from my personal perspective, since I care so much about termination, memory safety may also mean the program may just get stuck and never return. So memory safety is of interest pretty much for all other properties, if you're working in a language where it can be violated. So the usual caveat from theoretical computer science applies. All these properties are undecidable, and So sometimes we may have to give up and say, this program is really hard to understand. I'm not telling you anything about it. But if possible, we'd like to be able to give an answer automatically via some sufficient criteria. So how can we then approach the static program analysis? So the goal is to prove whether a given program has a nice property, or to find a witness that it does not have that nice property. And this approach is often done in two phases. In this talk, I'm going to call it the first phase, the front end, similar to a compiler. You take a program in a real-world programming language, and you would like to, the front end tries to translate that program to an intermediate representation that is desugared. So you don't have several different ways of expressing a loop, but you use a simpler language that will be simpler to analyze. And in this translation, some information may even get lost. But as long as you can be sure that what you've generated, if even that is safe, then also the original is safe. And that's good enough. The second part of the static program analysis approach is then the back end, which does the actual hard work of the analysis of the desired property. So this is where, for example, for termination, a ranking function will be found. Because the translation of the front end has preserved the property of interest, what the back end says carries over to the original program. So in other words, we start with a program in some programming language L. From that program, the front end generates an intermediate representation. Let's call it RP. And the back end will then tell us the result for RP plus a proof for that result that ideally can be checked separately. So what I'm now going to focus on is, what is that intermediate representation that we might use? And well, this is where now constrained term rewriting comes in as one possible choice. So the how to choose an intermediate representation for such a static analysis, one can take inspiration from proving program termination. So in early translations in the literature, for example, by Femke van Ramsdonk in the late 90s, the idea was take a logic program as input and translate it into a term rewrite system such that termination of the term rewrite system implies termination of the original logic program. So term rewriting system, let's see whether we can work with those. And first of all, let's see what are term rewrite systems. So what's term rewriting? Well, it depends who asks. If a mathematician asks me, I will tell them term rewriting, that's a syntactic approach for reasoning in equational first order logic. So I wouldn't mention programs there at all. I would rather take the logician's perspective. Then if a programmer asks me, I will answer the question slightly differently. I will say, okay, term rewriting, that's a desugared functional programming language that doesn't have many restrictions and also lacks some features of real functional programs. So term rewriting, if someone tells you something about term rewriting, chances are they'll be talking about first order term rewriting. term rewriting usually doesn't assume fixed evaluation strategies. You can choose which rules to apply, so there's no specific order, whereas in Haskell or Scala, the programming language forces you, okay, we're trying to apply a rule and we want to do a matching step. First try line 1, then try line 2, then try line 3, whereas term rewriting will happily grant you non-determinism. Anything that can work is allowed. Term rewriting in its simplest form is untyped, and it doesn't come with predefined data structures such as integers, arrays, all the things that programmers really like to use because it makes their life so much easier, and that for writing a concise definition is not so popular. So term rewriting is very convenient if your programs are over user-defined algebraic data types, inductive data types. So, well, as if inductive data types is what we're working on, we can represent numbers, let's say natural numbers, as 0, then 1 is the successor of 0, 2 is the successor of 0, and so on. So in principle, we can represent arbitrary natural numbers like that. We can write a term rewrite system that's with rules for plus. We saw them earlier today, to sum up two natural numbers. And if we want to compute, the triangle numbers via the sum, we can use plus as a helper function. So with such rewrite rules, we can compute, for example, 1 plus 1 equals 2 as plus of 1 and 1. Well, which rule might we use? The first one, plus of 0 and y. Nah, that doesn't match. 0 and s of 0, that doesn't go together. So let's try the second one, plus of s of x and y. Well, x can become 0, y with s of 0, and then we can replace the instance of the left-hand side by the corresponding instance of the right-hand side. We get s of plus of 0 of s of 0, or 1 plus 0, 1. And now we can use the first rule, and we get the result 2. Hooray! So we can also represent integer arithmetic with more complex recursive rules. So then you need to introduce constructors to represent also whether a number is positive or negative. It can be done. But there are downsides. So this has been done in program analysis tools. But then problems came up from the more banal as, oh, the programmer wrote 1 million in their program. And the program analysis tool ran out of memory when it tried to represent 1 million by a corresponding number of objects. So s of s of s of, and so on. So there are drawbacks to using classic term rewriting. There are reasons why we have to go beyond that if we really want to make an approach via term rewriting for static analysis of programs, if we want to make that work. So a major drawback is in the programming language, we have the domain knowledge. We know what an integer is. We know what plus means, what times means. There is significant theory. There are SMT solvers around that have all that knowledge, how to reason efficiently with numbers. But in this approach of saying, I want pure term rewriting, okay, then we must analyze recursive rules for plus, times, minus, over and over. And we don't get a benefit from all the separate work that has been put in by researchers in constraint solvers for all those arithmetic operations. So the solution that I would like to propose to you today is use constraint term rewriting instead. So what's that again? So in short, it's term rewriting with batteries included. So again, in the most basic form, it's first order. We don't impose a fixed evaluation strategy. We don't impose an order of the rules to apply, so we still keep some of the flexibility. But it really does make sense to introduce types. If we know that some variable stands for an integer, we may as well give it the type integer. If another variable is for a list, we may as well say that's for a list. Constraint term rewriting comes with predefined data structures, which can be in principle anything that is described in a first order theory. So integers, arrays, bit vectors, whatever your SMT solver supports, you can also combine with constraint term rewriting. So what you get is rewrite rules where you may have on the side constraints that can be checked by existing constraint solvers. So now we have a language that we can use to represent programs over user-defined algebraic data types and also predefined data types. So from a Java perspective, for example, not only can we represent classes, we can now also represent primitive values and arrays. So what constraint term rewriting gives us is a combination of systems, term rewriting on the one side and SMT solving on the other side. So different areas of automated reasoning join forces. Constraint rewriting as an idea is actually pretty old. So the oldest paper that I found is by Vorobyov, published at RTA 1989. So I think at the moment this is the only paper from the Soviet Union that I've cited. And in the following years, there have been a number of other proposals of what should a good constraint term rewriting language look like. And the approach that I think has gained the most traction is called logically constrained term rewriting. So logically constrained TRSs. Proposed by Cynthia Kopp and Naoki Nishida at FroCoS, of course. And this approach has been adopted pretty widely in the community. Last night, I asked Google Scholar, how many citations have there been? So far, it's 83 and continuously going up. So I'd like to tell you a bit about what can we analyze for logically constrained term rewrite systems. There is a lot of work on termination. This list is very much non-exhaustive. There is work on complexity, equivalence proving, confluence proving has become a hot topic recently, and reachability proving, or its flip side, safety proving. So if you're interested in one of these properties, corresponding techniques and also tools exist. So let's look at an example to get an idea of what is constrained term rewriting. So here I have brought a rewrite system with 3 rules. In my rewrite rules, I like to paint my defined function symbols. So what a functional programmer would call a function, I like to paint them red. I like to paint my user-defined constructors blue. And for predefined things like plus or 1, I left it black. So imagine we want to start running our program from L0. And we go to L1. So that's a classic term rewrite rule. But in the second term rewrite rule, we have added a constraint. We are allowed to use that second rewrite rule only if the number n is greater than 0. Let's look at a possible rewrite sequence. We might start with L0 of 2 and 7. Apply the first rule to make a step to L1 of 2, 7 and nil. Now we can use the second rewrite rule because 2 is greater than 0. So we are allowed to use that rule. And we replace 2 by 2 minus 1. So from 2, we get 1. We replace the 7 by 7 plus 1, which is 8. And we have just created a list element with 7 as the entry. And otherwise, that's an empty list. We can take another step using the second rule, because also 1 is greater than 0. Now the second rule is no longer applicable, but the third one is. And we reach L2 of the list of 8 and 7. So here, numbers like 7 and 8, formally they're predefined constants. So on the formal side, what we've traded in is we've got an infinite vocabulary, an infinite signature, because there are infinitely many integers already. But that's not such a problem in practice. So to prove termination, can anyone tell me why this thing might be terminating? So for a termination proof, usually something needs to get smaller whenever we apply a rule. And so that can only be done finitely often, then that rule is no longer applicable. There are indeed good tools. Now I'm using the tool of the FroCoS audience. So n is decreasing, I hear. And yes, I agree. So here we can take the perspective of, let's think about integers. And so which rules are harmful? Well, the first one, L0 goes to L1. We can do that only once, and then no more L0, so that's harmless. The third one is also harmless. L1 goes to L2, and then we're stuck at L2. But the second one, the recursive rule, here something would need to happen that can only happen finitely often. So n goes to n minus 1, n is decreasing. And if it's just a decrease, that can again go on infinitely often. N become, if there wasn't this constraint, n could become minus 1 million, minus 2 millions, and so on. But here we say n must be greater than 0. So we have the decrease against the bound, and that can only happen finitely often. So here we can reuse a technique designed for integer programs, also to reason about programs that additionally have algebraic data structures. So let's now talk about a technique for the backend designed for analyzing functional programs. The title of the section is a bit of a mouthful. So first, let's talk about why should we be analyzing termination in the first place? So for a program, we want the program to produce a result. And it's a nice property to analyze because we don't have to ask the programmer to write a specification. Generally, it's considered a good thing if a program or a function will always terminate. Then for another example, an input handler, which in itself is supposed to be non-terminating, your device drivers really should keep running, you still want the concrete handler to react. So when you move the mouse, something is supposed to happen on the screen. Back to the mathematical perspective. For a mathematical proof, termination in many theorem provers is needed. And certainly if they are based on induction, so that the induction is valid. there are even applications in biology, so biological processes, to prove that they reach a stable state. And those are actually variations of the same problem. So our input handler is a special case of a program. Its subroutine that is supposed to deal with, I've moved the mouse, is a program. Our mathematical proof, with a certain perspective, we can think of that as a program. And our biological processes are, in essence, a probabilistic version of a program. So research on probabilistic programming, one application can be in biology. An issue that occurred in practice was in 2011, there was an exploit for floating point parsers that was heavily used in web applications, namely the parser library. If you gave it a very nasty string, the parser would not terminate. It was quickly fixed, but it's a very cheap way of achieving denial of service if you just have to send a single nasty message with a string that will never be converted into a number. So let's talk about existing translations for termination. I mentioned a few, I mentioned the one by van Ramsdonk, but in the meantime, there are many more. So there is demand. Now, about proving termination. What I'd like to tell you in the next minutes is about proving termination for call by value evaluation strategies. So here comes my research interest in specific evaluation strategies. And the reason why I care about call by value, a number of relevant programming languages use call by value strategies. So OCaml, Scala, if we're thinking about functional programming. And analyzing with regards to specific strategies has the benefit you get more powerful tools, because you can make stronger assumptions about what can and cannot happen. So what I'd like to show you is an intermediate representation for higher order functional programs. So namely constrained higher order rewriting as an intermediate representation using call by value evaluation. For the termination proving, we are using an adaptation of the dependency pair framework to this that was originally invented for classic term rewriting. René did his PhD on the topic. And in the meantime, it has been lifted to higher order rewriting, to logically constrained rewriting, and to combinations thereof. So let's think about what makes for a good intermediate representation. It should be good for automated reasoning. So we don't want any lost in an encoding that as we've seen with representing the number 1 million by 1 million symbols S that are nested around a 0. And ideally, we would like to be able to express language features directly. So, for example, well, this is the other side of the coin. We'd like to be able to say the language has the number 1 million. I want to be able to write that down directly. So what's available? Well, we saw earlier, term rewriting systems are good for algebraic data structures, but have their downsides because you must do some not quite so natural things to represent numbers. On the other hand, our colleagues, if you attend the CAV or TACAS conferences, papers on termination proving in the last 10, 20 years are often about some form of integer transition systems. They take a program and translate it to a mathematical representation that does not have our user-defined constructors, but that very much does have integers and operations on integers. Here, for example, I've brought an implementation of the greatest common divisor function over positive and negative numbers. And then logically constrained term rewriting combine the systems. Term rewrite systems, integer transition systems, and broadening the idea of to arbitrary logical theories. And what I'd like to talk to you about today is logically constrained simply typed term rewrite systems. So the acronym gets longer and longer. This is a very careful extension of LCTRSs into the higher order world. So we do allow for functional arguments, but even a lambda abstraction is too much. And let's not even think about dependent types. So that, of course, would be great to have in a future extension, but we're not there yet. So here I've brought you a function GCD list that takes a list of integers and computes the GCD of all the integers in that list by just computing a fold of the GCD function with the neutral element 0. So that's very functional programming style. So there is a bit of a wrinkle in the literature about proving termination. Call by value is what many programming languages use, but there is quite a lot of literature about something closely related called innermost rewriting. So I've brought you a small toy example to illustrate the difference. Namely, the first two rules compute the factorial recursively. Factorial of 0 is 1. Factorial of x, if x is greater than 0, is x times factorial of x minus 1. The third rule is highly artificial. G of x goes to g of fact of minus 1. Ooh. Okay, let's see what happens. In call by value evaluation, let's say we want to evaluate the term g of fact of 1. Well, with call by value, okay, fact can be applied to a value 1. So all numbers are values. Gives us 1 times fact of 0. Fact of 0 evaluates to 1. 1 times 1 evaluates to 1. And now finally we can evaluate g of 1, which gives us g of fact of minus 1. And we're stuck. Fact of minus 1 is not a value. It's an application of a function. And call by value rewriting terminates. So that's what's used in programming languages and what we want to analyze. But in the literature, you find a strong focus on innermost rewriting. And innermost rewriting now uses a slightly different perspective. The first rewrite steps go in the same way, but innermost says you're allowed to use a rewrite rule if at some regex, if no strict subterm is could be evaluated. So g of fact minus 1, well, fact of minus 1 is a normal form, can't rewrite that. So we are allowed to use the last rule over and over, and it doesn't terminate. So we've introduced a slight technicality to work around this issue so that we develop a DP framework for innermost constraint rewriting, but it's still useful for call by value. We propose a transformation so that if we say, oh, in the last rule, I add a constraint x equals to x. Now the semantics of LCTRSs say if you mention a variable in a constraint, that variable may be instantiated only by values. And fact of -1 is not a value. So now we can feed this time rewrite system into an analysis tool for innermost rewriting and get the answer that indeed terminates. So side note, that is a bit of a hack. It enforces call by value only for theory sorts, but it does make our analysis a little stronger. And it's why in the following we'll talk about innermost rewriting. So to analyze termination of a rewrite system like this one, which consists of the GCD lists rules, including fold and GCD, the standard approach to prove termination is using dependency pairs. In our higher order language, the corresponding adaptation is called static dependency pairs, which are essentially the function calls in these rewrite rules. So what we need to show is, let's say this thing was non-terminating, then there would also have to be an infinite call sequence. So an infinite sequence of function calls that leads to the non-termination. The corresponding candidate for non-termination, labeled here in magenta with a sharp symbol, are, well, GCD list may call fold, and that may happen infinitely often. So GCD list calls fold, and GCD down here does not get the hash symbol because this is just for terminating applications of GCD. And separately, we analyze GCD list calls the GCD, and this one may then be the cause of non-termination. Fold may never even be the cause of non-termination. So each function call gets analyzed separately. The dependency pair framework now works on what is called DP problems, a set of dependency pairs, potentially harmful non-terminating function calls, and a set of rewrite rules that are not considered harmful, that we only use to evaluate arguments in terminating evaluations. The DP framework now is about take one of these DP problems from the current set of problems, apply what is called a DP processor termination technique on it, and if you've been able to eliminate all the DP problems, then you know that thing is terminating. So existing processors include adaptations from the literature. And I'd like to show you some new processors that work specifically for the innermost setting. So about existing processors. So the problem that we now need to analyze is these 6 dependency pairs. And for the processors at hand, we don't need to care too much about what these rules actually look like. The first processor is called the dependency graph processor, tells us which of the function calls may follow one another. For example, up here, GCD list calls fold, and the next function call would then have to be a fold call. So we have only a single rule for fold, or a single dependency pair for fold. Fold calls fold. And so GCD list calls fold, that can be done just once. And fold calling itself, that could be done in principle infinitely often. What's now dangerous for termination or for non-termination is the cycles in here. So the dependency graph processor splits the problem into the cycles in the dependency graph. So here we have 3 cycles, and we can analyze them separately. So fold calling fold. Well, why is that terminating? The reason comes from classic term rewriting. The last argument, cons of xl, gets replaced by L, and that's structurally smaller. So we can conclude this dependency pair does not cause non-termination for reasons from classic term rewriting. The next dependency pair that we might analyze is this GCD dependency pair, where what changes is the last argument of the call. N is replaced by M modulo N if certain constraints hold. And we can now use S&T solver style reasoning. If the constraint holds, then it is the case that N is strictly greater than M modulo N, and N is also bounded from below by 0. So that again gives us a valid termination proof. And the third DP problem can be handled similarly. So our running example, we've proved its termination. A few words about new dependency pair processors. So consider this example of a function that essentially takes the idea of a fold and drops a few elements before between applying the function call. So it simultaneously drops elements and folds the remaining list. So the troublesome DP problem here is has a dependency pair where in the last argument we have cons of XL, so we have a list that is not empty, and then we drop some elements in the last argument. So there is a powerful processor that can show things like this list is greater than the result of drop NL, but it gets stuck with this rewrite, with the last rewrite rule from R. So we keep carrying those rules from R around because we must show that the terms don't sneakily get bigger when we use them. Problem here is we have an application of a functional variable, of a higher order variable to some values, and then all bets are off. If you have one of those on the right-hand side, you've essentially lost if you must deal with that term constraint. You must somehow be allowed to ignore that. Here we are allowed to ignore that because, oh, but our DP problem doesn't use that defolder rule. That only uses the drop rules. So drop doesn't call defolder, so we can ignore defolder. And what now remains can easily be handled by existing techniques. Another variation, we can fold in 2 ways. We can also have our application of F inside defolder, which of course gives us a troublesome DP problem, where now we have F of Yx in the dependency pair on the right-hand side itself. All rules are become usable because F could be anything. Now we are allowed to temporarily disregard some argument positions. So here, for example, we say, let's just look at the last argument. And we saw already earlier, existing techniques can show a non-empty list is larger than what we get from dropping something from its tail. And we can also solve this problem. Very quick words about chaining. So this is an imperative program here in Python syntax. The corresponding dependency pairs, essentially the translation from the imperative program to rewrite rules takes every instruction in the code and makes a rewrite rule out of that. Here, we've directly transformed the rewrite rules to dependency pairs. And this already shows us there are many instructions in here. This leads to many rewrite rules. And the reason for non-termination now is, for termination, is in different rewrite rules. We have the bound. So intuitively, x minus I gets smaller and smaller until it hits 0. But the constraint for the bound is in one dependency pair. But the increment against the bound x is in a different one. So that's already beyond techniques or many basic techniques. So what we can now do is to simplify. We can just merge two consecutive instructions. So what we then get is what also looks like what a human would have used as a translation. So via this so-called chaining of consecutive dependency pairs, we've simplified the problem. Now all the information that we need to conclude termination is in a single dependency pair, and the integer mapping processor can show termination. So this approach carries over to open world analysis if we want to use this program in a combination with existing libraries. For time reasons, I may skip the experimental section, which essentially says this works is a step forward, but specialist tools are currently still better than what we've come up with. If we are working on only first-order integer term rewriting systems, the specialized tool approve is stronger. If we are working on only higher order systems without integers or other theories, the specialized tool wonder is stronger. So you can find out more about what we've done here in this FSCD 2025 paper. And if it's okay time-wise, I'd like to make some very quick words about a transformation from Scala programs to constrained term rewriting. So the background is in Lausanne. They're developing the stainless verifier for Scala programs. Open source tool, you can find a lot of information there. And similar to other verification environments, the verification approach requires functions to be terminating. And of course, provably so. So in Scala, we might have here a slight simplified student example for data type of formulas, which have true and false as constructors, not of a formula, but can be a formula, and imply of two formula arguments can be a formula. Then a student might write code for a Scala function that's for evaluating a formula to a Boolean. So how can we prove termination of something like that? So this is recursive, so it might not terminate. Well, Scala supports out-of-the-box manual measure annotations. So the programmer can write something like decreases t.size, which in this case does not prove termination because the verifier gets stuck on the last rule where f is called on not of the left-hand side of an imply. Recently, a type-based measure inference was introduced to fill in this bit automatically. Very recently, we introduced something like a semi-manual approach called measure transfer. You've got a similar looking program for which you have such a measure that decreases, try to port it and see whether the verifier swallows it. What we're doing here is to translate this function to LCTRSs. And here we have a simplified version of our LCTRS, which can easily be proved terminating. So this is perhaps the minimum challenging example that can now be proved terminating. we've run experiments to compare these methods on examples from auto-grading papers. Here the gist is, so these are instances that cannot be handled by measure inference. Well, the sigma benchmark cannot be has higher order arguments, and at the time we chose a proof as the tool and input format of choice. So it had to give up on that. But overall, thanks to the use of LCTRSs, we gained something over the semi-automatic measure transfer and a lot over the inference approach. There are some limitations. For example, we haven't yet taken care of bounded versus unbounded integers. We don't yet support higher order functions. Support for lazy values is missing. And the encoding of the line-by-line pattern matching in Scala is currently a bit complex. It's essentially quadratic in size of the number of cases. And I'm looking forward to the next talk to learn about pattern differences, which may help us to come up with a more efficient encoding. So to conclude that last part, this is work in progress about using constraint rewriting to analyze Scala programs. You can read more in our WPTE paper. And to wrap up the whole talk with the take-home messages. So the workflow I propose for static analysis is take a program, translate it to an intermediate representation, analyze that, and you get the result that carries over to the original. Constraint rewriting is a very versatile intermediate representation that can also be extended. If you need more features, just add them. You should just have an idea of how to automate reasoning about them. I've discussed LCTRSs with a recent extension to higher order. We can analyze a variety of properties, and there is also a number of tools out there that you can run to analyze these properties. So my question to you is, can your programs, your specific language flavor, be translated to logically constrained term rewrite systems? If so, the existing tools may do the rest of the work for you. Thanks a lot for your attention, and apologies for the slight overtime.